Well, good day, everyone. This is Fred Schankelberg, and thanks for joining me today for another Ascendo Reliability webinar. Today, I'm continuing the Fundamentals of Reliability series. I actually put it in the title here inadvertently. It's really Fundamentals of, pause, Reliability Performance Monitoring. And I thought about using metrics or measures or objectives or whatever. To me, it starts to be all pretty synonymous. Whatever you want to call them, is we often set goals and we work to achieve those goals or measure against those goals, those kinds of things. But performance monitoring is, I think, a bigger topic, and I wanted to spend a little time with you today and talk about that. And so let me find my cursor here. There we go. So monitoring is that the idea, and I was trying to find who made the quote, maybe somebody online knows it, is that we do what's measured, or that notion that people pay attention to what's being monitored or measured. And I think it comes from the concept in business of management by objective. We set all these corporate objectives and it gets rolled down to our individual performance reviews and we have all these objectives. The theory is that we pay attention to that because somebody else is paying attention to it. And years ago, there was a study in a factory where they were experimenting with, excuse me, the lighting within the factory. And they were looking at, would the lighting, increase in lighting, which would be adding an expense to the factory floor, improve productivity. And so they did an experiment, they added a bunch of lights, they turned it all up, and they measured productivity. And then they took all the lights out, and they measured productivity, and it went up again. And so the result of the study wasn't anything to do with lights. It was that if you're measuring productivity, people will pay attention to being productive. And so it's that basic notion is one of the fundamental reasons that we set reliability requirements. Is our customers have these expectations, right? And so we're trying to anticipate those expectations and set a tangible specification. In some industries, we might call it an objective or a goal or a specification or something we want to track. And they're going to judge us. They don't use any particular metric. They've got a copy of your product, and they're going to say, hey, it works or it doesn't work. It's reliable or it's not. Now, over time, customers that deal with many of our products or have a whole fleet of our products, excuse me, have a bit more information to work with. And so that part of our setting objectives is a way of reflecting what our customers' expectations are, and to, as they judge our products, is to get a favorable review or favorable opinion of it. Now, the other part of monitoring what we do and tracking performance, and whether it's looking forward as estimates and predictions, or if it's looking at field data and actual performance, or test data, we often use, is one of the questions I heard in a product development team I worked with was, are we there yet? It's very similar to my 2-year-old and the 3-year-old in the back seat. Are we there yet? And it's in reference to, is the product meeting requirements? Is it meeting our goal? Have we arrived at a good enough product that we're ready to ship it? Or do we need to work some more to improve it? All of the stuff we do in reliability should be connected to decisions. And you're going to hear me say this a few times today. And the best way to influence those decisions, to provide meaningful information to inform decisions related to reliability, is with data. It might be a study on a new material, it might be the results of an accelerated life test, or it may be field data analysis providing a life distribution. Root cause analysis, on and on and on. All the things we do generates data and hence information that can be used to inform decisions. And that's really the thrust of why we do performance monitoring, tracking our measures. So in your organization, let's jump into the chat window. How do you talk about reliability? How do what do you measure? What do you monitor or track? You know, as my voice is warming up here, I'll take a quick drink of water and give you a chance to chime in. Defects. So Mark, I'm not sure what you mean by in started samples. Is that like early life failures or infant mortality type defects you're looking at as a function of time? Hardware failures. Well, Sean, what about software failures? Do they upset customers also? Let's see. How'd you that? Well, I won't talk because you can't hear me there. So let me see if I can get that in. Let's see if I can get it in here. Eight four five 2390. So hardware failures, software failures, customer complaints. Good. Dan, I've seen too many organizations that do just confirmed failures and then ignore customer complaints, which sometimes could be um, uh, intermittent or difficult to reproduce because you're not in their situation. All those kinds of things. So it can vary quite a bit as a function of time. Good, good. Test programs. Yeah, yeah. I know program managers are often very interested in, well, how many samples do I need? And I find that you have to ask for twice as many as you need oftentimes. Availability. Yeah, ready to go when you need it. Yeah, number suspension. Oh, excellent. All right. It varies quite a bit, and we track reliability, and it's usually tailored to your particular industry or your particular circumstance, and it may change with different products, whether it's a new technology or if it's a standby that you've been using for 30 years. It could and should vary depending on what questions you're trying to answer. Now, one that's generally universal, and I didn't see it in the list, is profitability, warranty expenses, and how those relate. And it's obviously related, but just the cost of unreliability, and that larger notion of cost of unquality or cost of quality of the other side of it. Um, they often play as a factor into many of those things that everybody's been mentioning here. All right. So there are a lot of different measures or metrics that are out there, and I'm going to talk about a few of them just in brief, and more importantly is how they make a difference, how they relate to the decisions that we're trying to make. Yeah, I agree, Mark. It oftentimes in an organization, one of the tricks I've learned is people pay attention to the cost of the product per unit shipped. So if I'm making a laptop, it might cost $500. This is probably old when the laptops cost $2,000, but it might cost you say $500 in materials and assembly costs to put a piece of equipment together. And we worked out what the warranty per unit shipped was, and it was $100. It was just about as expensive as the most expensive component in the device. And we're paying attention to the most expensive components and looking at cost reduction opportunities and ways to shave a penny here or a nickel there. And nobody was tracking warranty per unit shipped. We had this big warranty number or percent of net revenue, yet when you broke it down into the cost per unit shipped, it became salient as how important it was to actually pay attention to the reliability part. The trouble is it's not in the bill of material. You can't see it. It's not on the benchtop anywhere. We don't see warranty cost in prototype testing. We see failures, but then we have to translate that into what that would actually cost us. And so some of those decisions we deal with, tying the money into it oftentimes makes it very real. Yeah, and support. The call center and field service and the reverse logistics system, all of that adds up. The one that I find, Robert, that most people forget is the cost of engineering that deal with products that have already shipped. So some organizations actually put in a whole team to shield the design team from having to deal with it. Right? There might be a field service engineering team or a continuous improvement engineering team or whatever we want to call it. Even if they don't have that, director of engineering after director of engineering has told me they spend approximately 25% of their engineering time dealing with products that are already fielded, things that need to be fixed or improved, and usually fixed. And that's a huge expense when you look at how many engineers are developing products, and a quarter of their time is spent fixing what they should have got right the first time. And so that might be a subject to a whole nother discussion. All right, I promised I'm not going to talk about MTBF too much, other than just to say, if that's how you, and nobody mentioned it here, I think it's a lot of regulars, so that you know I don't take well to this metric. It's an average, right? It gives you the average time to failure. It's not terribly useful. Very few people understand it. Most people misunderstand it and misuse it, those that we work with. So what can you do if you know MTBF? What decisions can you support? Yeah, thanks, Mark. Yeah, and you probably, I mean, we use measures and metrics and we do predictions. People have done predictions for years and they come up with this MTBF value. Or you track down a data sheet and there's an MTBF value on it, say for a pump or for a motor or for a bearing. Now, most of you know that I would say you really can't make any decisions based on knowing MTBF. No, to be fair, sometimes that's all we got. That's all we have. And I almost always invert it right away and get failure rate, and over a relevant period of time and try to convert this to a reliability value. Yeah, sparing decisions. Yeah, Sean, you know, if I've got 10 vehicles and I know that I have about one fuel pump per year fails, I don't need a ton of spares. I just need one, and hopefully I can replace that pretty quick. On the other hand, if I need spares quicker on average for a mixed fleet, then it really becomes a difficult problem. And so the hard part I find with sparing an MTBF is that, well, what if I need more parts up front if I have early life and wear-in type failures and fielding a new fleet, or if it's a wear-out, if all of my vehicles are 5, 6, 7 years old, the types of spares and the number of spares would be different than if they're all relatively new. Now, in most organizations, I have some new, some old. It's a real mix, so it starts to average out. And in those cases, yeah, MTBF, don't quote me on this, reflects this average arrival. Now, having said that, it still has problems with just people understanding what it means. It's not a failure-free period, blah, blah, blah. So let me sidestep that for a moment. Yeah. The MTBF is so commonly used, and we make so many decisions based on it, that you need to know where the limits are of it. It's an average. It's not telling us the changing failure rates. It's not telling us if it's coming up or down. it it is so widely misused and misunderstood that it has little actual value when we use it in conversations even. So the decisions that MTBF support, there are some. I grant that. With caution. And there are better ways to do it. So I would say stay away from it when and where you can. All right. And so reliability. Why don't we just use reliability, right? The hard part is that reliability has a common language definition of you can count on them. It's dependable. Different than the way we would define it in technical terms. But in technical terms, the way O'Connor and Kleiner in their book defined it, which is very common to the definition found in most textbooks and in most places that I've seen it defined, it has four elements. What's it supposed to do? What's the probability that it does it successfully over some duration within some environment, including how often it's used? And so the reliability is a probability that it'll work for some time, right? It's just, although as soon as you mention probability, the room of engineers' eyes glaze over, as we so fondly remember our probability and statistics classes. And so it's not that scary. It really is, if I have a vehicle and I have a Toyota Highlander sitting in my driveway, what's the probability that it'll operate for 3 years in the way I use it in here in Northern California without a major failure? And I'm thinking that I still need to change oil and it might need to put some new tires on it, normal maintenance, but I won't be stranded on the side of the road. Now I judge it as that it's a very low probability that I'll get stranded. So it has a very high reliability over this 3-year period. Now, when I consider, will this vehicle work for me for the next 30 years? Now I'm starting to think the reliability of this is going to drop off. Timing belts, electronics, the valves, the muffler, fuel pumps, on and on and on, is going to take more and more maintenance to do this. And the likelihood that one of those critical systems fails and strands me on the side of the road would increase at some point. Now, hopefully that's well after the 3 to 5 years that I expect to hold onto the car. Yet, it's a consideration for any product that we have. And it's that changing nature at these different time intervals that we want to deal with, right? And so the notion of just, well, what's the probability that it'll succeed? Will it install correctly? Will they get it up and running? The early life failures, say the first month or after installation, should have a relatively high probability of success. Warranty period for most consumer products is of interest directly to our finance groups. Well, what's our probability of success? And the converse or the complement of that is what's the probability of failure over our warranty period. We could quickly calculate what's the expected number of warranty claims we would have. And then how long does a customer expect to hold on to a product? Let's use 3 different durations and their associated probabilities. It helps us to deal with a very simple question. How many are going to last 5 years? And so if I know that 98% it's 98% reliable over 5 years and we have 100 of them, well, I expect 98 to still be working at the end of that period. And it's hard to misunderstand. And it's why I like it so much better than MTBF and other single point failures. Now you can get more sophisticated and give them a plot, say a log normal cumulative distribution function plot, or a Weibull reliability function plot, or a gamma function, or whatever distribution is appropriate, and define it over the entire timeline. And in some cases, that's actually very important to know. But most of the time, we just want to know it at a few different time points. And so they're always couplets, the probability and the duration. So if we know the reliability of a system, right, and we have some, maybe even a life distribution or even just at three different points, what decisions can we support there? And go ahead and jump into the chat window. I'm going to see if I can help Hojat here real quick. Yeah. So as a customer, if I, like with my Honda, I've had very fine performance over the previous vehicles I've had. So now I would consider I'm a bit brand loyal. I'm staying with the Toyotas. So it has influenced my future purchases. Um, yeah, David, the finance guys, if I know that 98% are going to survive the warranty period and they can figure out the cost per failure, they can appropriately set aside warranty costs to plan for that. Yeah, warranty work. The other decision here is it good enough to ship? Is the design reliable enough to meet our goals? If we set a goal of 98% at 1 year, are we there? Does the internal reliability model we have support that we're at that point or not? Is there a key failure mechanism? Is that accelerated testing give us an answer? So if we have an answer we're at 90% reliable at 1 year, our goal is 98%, I can make that decision. Now we could use MTBF, but be cautious. Depending on the nature of the distribution under it, you could flop that decision very easily and make the wrong one. Reliability takes a lot of that away and helps. It still can make mistakes, yet it sure makes it easier to make comparisons. So I use it for that. Yeah, obsolescence. Like my vehicle, if I ended up keeping it longer than 5 years and I'm tracking my time to failure information, it's like the car I had in high school. I learned, this is my first real reliability um, education, was I was getting maybe a week or 2 weeks of trouble-free driving with this old car. I spent as much or more time then in the shop changing things and fixing things and fine-tuning things to keep it running. And as that escalated, as more and more things fell off or broke or failed, it became painfully obvious that I was spending more on maintenance than I was on anything else to deal with the benefit of having a car. So ended up selling it. Unfortunately, my dad didn't buy me. I didn't negotiate to get a better, higher reliable car. He ended up with another fix-up special that I think he was trying to get me into auto mechanics. But anyway, yeah, we can know all kinds of things about our equipment and our systems and everything from sparing to obsolescence to future purchase prices to uh, uh, maintenance time to the decision, should we start production? Are we ready to ship? What's the risk we're taking? All of those decisions can be supported by knowing the reliability of your program. Now, I'll mention availability briefly. It's similar to reliability, except now it's for repairable systems, and it includes the maintenance time involved. So if we have a failure, we can repair the system, much like my car, and if the availability is high enough to be of value to us. Now, my old car in high school was not all that available. It was probably a 50-50 shot that it would start in the morning, which was a reliability issue, and then it would be, a couple of hours to a couple of weeks in repair. So just the option to go out and run to the store or get to school was seriously degraded because of its lack of availability. But the basic idea is that does it work when we expect it to work? And knowing that is very similar to the type of decisions we would have with reliability. Is this the right piece of equipment? Is our capacity uh, planning for a factory, for example, if we know our bottleneck piece of equipment has a particular availability and uptime, we can do capacity planning and throughput planning. Uh, if we're looking at making changes, we can measure the changes in availability to see if the new maintenance strategy is improving our uptime or not. Um, we also know, is it ready to go on live on production? Is the system robust enough, and do we have the right levels of redundancy in it, and so on. So a lot of the decisions we make are a little bit more sophisticated than just reliability, because they include, well, are we maintaining it correctly? Are we efficient at that side of it? Is it possible to do the maintenance? Do we have the appropriate diagnostics and tools and training and equipment available to execute repairs? So a different set of decisions that it supports, but availability can also be time connected. We don't need to use MTBF divided by MTBF plus MTTR, the classic availability formula. We can use what's the probability of success, the reliability at time t divided by reliability divided by time to repair. And let's sort out, is it more available at 1 month duration or 1 year duration or longer or at different time periods? So use it appropriately to make better decisions. Um, Process capability. Let me see if I can grab my, um, I want to, oh, it's not going to let me do my pen. Oh no. What did I do wrong? Yeah, it's just, well, anyway, I'm going to have to wave my hands and hopefully you can see it. I'm sure most of you are familiar with process capability and CP and CPK kind of measures. This is one that I don't see us in the reliability world tracking and measuring as much as I think we should. Now, those that have been on these sessions earlier or previously know that my background in industry started as a manufacturing engineer, as a plant supervisor, and then as a manufacturing engineer. And the plant I worked with, we did a lot of statistical process control. We worked with our vendors to understand their processes. Process stability and process capability was more important than just shipping products. The product that we were making was expensive, and if you made bad products, there was no repair cycle for it. It was just scrap. And so throwing away a $20 a foot cable that you have 10,000 feet of got to be pretty expensive pretty quick. And so we paid particular attention to process capability and used it as a measure of not only our yield, but it also forecast the performance in the field. If we were making products that were close to the edge of the specification, and given the amount of measurement error that we had, it still ran into problems in the field. It wouldn't last as long. It wouldn't perform as well. Now, this is pretty intuitive to most reliability professionals. Yet, are you working with your teams to understand process capability? And so the idea is that CP and CPK in particular, allows us to compare our specification to the variation of what we're producing or buying, for example. And so the idea is, Danielle, the availability formula, yeah, there it is. Mark's got it. It's not the one I recommend. I would, instead of using MTBF and MTTRs, use the distributions and include time in those calculations. So a reliability block diagram with each block being a distribution is, I think, a much more useful process. So CP, CPK, I was going to draw the specifications and the normal curve within it and that kind of thing. Sorry about that. Oops. Get my cursor back here. For some reason, wasn't able to get to my drawing tools here today, so not sure what the deal is with that. So if I know process capability, what decisions can I make? Let me pause here for a second, let you catch up with that in the chat window. And I've got about, I don't know, 3 or 4 decisions that are unique to knowing process capability. Let's see how well you do. You didn't know there was going to be a test today. Well, it helps. I think, Jim, that's an output of knowing process capability and focusing on it is to reduce variability, improve your product's robustness and its yield and throughput and so on. Those count. Process capability allows us to, do we have the right tolerances on our parts, on our specifications? If I'm machining a part and the style of machining is not capable of producing parts within quality control, exactly, Hojat, then we need to either change the design or change the specifications or understand that we're going to have loss both in yield and possibly in its performance in the field. So tolerancing is a key part of it. Another is comparing vendors. If we have 2 sources for a part and one is a CPK of 3 and the other one's a CPK of 0.5, there's a financial consequence to picking the one with the lower CPK. We're just going to have more problems and all kinds of problems. In some cases, it's a latent defect. It's something that gets into our product and manifests later and affects the reliability. More often, we affects just our assembly and yield processes, which has a cost in itself. But process capability is one of those measures or metrics that gets down into the components and into the dimensions of our products and details of the specification, yet allows us to determine the robustness of our design given the assembly processes and manufacturing processes we plan on using. And so that affects the reliability performance. It affects the functionality of our products in the field and their perception in the field. So it's another one of those measures that should be in your dashboard as you work through in the reliability field. So what other measures do you use? And what other types of ways do you deal with reliability performance measures? And I saw customer complaints earlier. I remember one group. Is the only time they knew they had a real problem was when the manufacturing line was down, and the vice president of one of the vice presidents was calling. Then they knew they had to deal with it. I guess everything short of that was just normal business, which was kind of sad. So their measures were who's calling. So a part of what we want to do in all these monitoring processes is, well, what do we need to monitor? Now, these measures are good in and of themselves in a generic way, yet making sure that you're measuring the right elements of that, getting data that's actually useful for you to make decisions is a key part of setting up these measures and metrics. The reliability and availability, process capability are good starting places, but if that set of information we're gathering can focus on the areas that I typically call red flag items. There's those areas that it's a new material, it's a new vendor, it's a new customer base, it's a new application. Usually when you hear the word new coming from your marketing group, it's time to pay attention. There's probably an increase in the risks of failures of our products. And so monitoring reliability, availability, or process capability are ways to identify where are those risks, and then are we on track in mitigating those and in dealing with those risks. An entire risk management plan may be appropriate in some cases, and reliability and availability and so on fits into those programs. Yet it may be focused on the overall system, or it may be focused on, say, the power supply, my favorite subsystem of any uh, product because it so often fails. The other part is that as we're setting up and working through what we're going to measure and what's the information that's going to feed into it and what level of detail is involved, is this fit with making business decisions? Now, for a long time, I felt that reliability was what we needed to do. We needed to make a very reliable product. We needed to make it more reliable. And I just didn't understand these product teams ignoring the sage advice to make the product more robust. And it's over some years, takes me a while to learn things, I guess. It was they still needed to ship on time, and they needed to make money doing this. And so getting it reliable enough, along with the other business objectives, such that reliability allowed us to create a profit, to meet our cost targets, to meet customers' expectations in balance, was appropriate. And so as we're setting reliability objectives, we may want 99.99% reliable over 1 year, yet the technical feasibility of that may be just lacking. We just may not be able to get there from here. And so it's a balance between what's our technical capability, our costs, how long before we can develop that product, all of those things that may force us to say, all right, 95% reliable is appropriate, given the market that we're in, given the business that we're in. And so balancing that with business is always, well, it's not always, you just need to do that. If the metric isn't tied to decisions related to your business, it's probably not really worth tracking that metric. So if I'm tracking field failures and I'm looking at failure rates and reliability as products are with our customers, the obvious business impact is warranty costs or call center calls or support calls or support costs. Yet there's also the business of the brand promise of our marketing effort, the cost to acquire a new customer. If we're getting bad reviews because of the shoddy reliability performance of our products, that affects more than just your warranty cost. So connecting those things helps us to inform those reliability decisions that we're making in balance with the other priorities within the organization. And then the one that we often talk about, but we don't measure very often, is customer expectations. And the hard part here is that it often changes. So the definition of reliability has functioned. Customers want more functionality with each generation of a product. Probability of success, that it should just work. Customers tend to expect a higher and higher reliability performance as products mature in the market, as generation of products come out. Consider the first phones, cell phones we had versus what we have today, and how much more robust they are, and coupled with our expectation that they should just work. And then the other part is duration. Years ago, it was for a car, it would be 2-3 years. I think that's what my dad's mindset was, that it's every 2 or 3 years he was getting a new car. Where to now it's a bit longer, and I expect in the future it'll be even longer. And the same with most products is that we expect them to have a longer duration, basically to be more robust in general. But then also there's the people are using them in different environments and exposing them to different stresses than we ever imagined they would use. So customers' expectations evolve over time, and given the world that we're in now with review sites and with Yelp and online comments and platforms for people to say, hey, this product was really great, or this product was really bad, and here's why. Here's photos. or video, the, the, the consequences or the benefits are there and much more visible than they were 30, 40 years ago. And so expectations are being informed not by our marketing teams, not by simply word of mouth at conferences or in business circles. It's being informed by the conversation on the net and what's going on. And so part of keeping track of that and monitoring customers' voice is as important as tracking warranty costs, because they can have it can be a precursor to problems with your product. It can also be a signal that you're not meeting those expectations, or vice versa, you are meeting those. So looking for those things to help us connect our metrics and measures into improving the decision making in our systems. All right, so how many of you remember, or more so, how many of you have actually used a quality functional deployment, the house of quality, to connect reliability expectations to specifications? And it's not meant to be a trick question. I imagine many of you are familiar with it. Yeah, so Frederick, you did it once. I mean, was it useful? Yeah, and Mark, sometimes we do have very clear specifications from customers. Some industries, they come in with basically saying, here's exactly what I want. Here's all the specs. They might even say, here's how you're supposed to test it. I always look at those very closely to make sure they're actually relevant and useful. Yet some customers are very good at it. Some customers in some markets are not very much at all. Yeah, and Frederick, the idea is whether you use QFD or some other system is, well, how do we connect those two things? If we don't have the luxury of the customer saying, here's my requirements, how do we do it? But I think the general thought process, whether we use a formal house of quality, but just the thought process of, well, here's what the customer wants in customer terms, right? The marketing guys tend to know this stuff. They want it to just work. Well, as an electrical engineer sitting in my office and trying to design a power supply, knowing that the customer wants it to just work, I can assume that. I get that. They just want it to work. But what do they mean by that? Is 90% reliable okay? Or is the consequence of failure unacceptable and we need to make a high availability system with hot swappable power supplies, for example? So how do I interpret the customer's expectations into reliability or engineering specifications, including the reliability pieces of it, right? And so there's plenty of stories about this. One, I was dealing with a team that was very used to making a very reliable printer. They made inkjet printers, and they make very reliable printers for business settings. And they were being tasked with moving into more of a printer that would compete with offset printing. So very high volume, very low cost in more of a factory setting. And they were struggling with trying to make that large, complex piece of industrial equipment reliable. And what was a breakthrough for them is realizing that we don't need to make it reliable as long as the parts that fail are easy and quick to fix. If we can snap in this part, or if we can clear jams very fast, or if we can not cause damage when XYZ goes wrong, it keeps the repair time very, very small. And if we can design it such that the operators can execute vast majority of the maintenance on it, the availability goes up. And so they were hearing that customers they had volume, so many magazines prints per day and all these other volume type requirements. And so they translated it as a reliability requirement. And they were trying to force this equipment to be an ultra high reliable device. But once they realized that they could get the repair time close to zero uh, or very small, it allowed them to meet their customers' expectations of throughput, of number of pages printed, for example. And it made a difference in how they designed their product. So the decisions was informed by fully understanding what the customer was trying to do and being um, interpreting that into these reliability related specifications. Yeah. Yeah, and it's a good point, Mark, is that it's, do you want to go worst case with your customer's expectations or some percentile of that? Where's the balance point of that? But also, what's my throughput? What's the formulas? What's the payoffs? What's the trade-offs? And so on. So the hard part with product design is that we can always find a harsher environment that only one person uses on one afternoon a year. Yet, do we want to design a cell phone that can survive that? Or a cell phone that works for the vast majority of people and we deal with the very few failures that we may see? You have to have a lot more information, right? And combination of understanding the distribution of your customers' expectations in use environments and usage patterns and so on. And then enough information so that you can make informed decisions. It's hard to do. Yeah, exactly. A good example, Mark, with the driving. It's, you know, if you need a vehicle that can do that, you buy a vehicle that is designed to do that. You don't buy the standard vehicle off the car lot for suburban commuting kind of things. If you need a military grade vehicle, well, then it's a different set of specifications and different expectations. Although we see it more and more often as people are using their um, off the lot SUVs for some pretty, and then you see it in the advertising. I saw one last night where they're driving over this granite stuff up. I'm trying to figure out where it is in the Sierras. Um, a beautiful area, but they're driving off-road with the standard vehicle, and yeah, that doesn't always work. We don't have that much clearance a lot of times. All right, final thought here, and then we'll wrap this up. And I apologize, I'm not able to draw, so I don't know what I did wrong that I can't get my drawing tools to work. A Pareto analysis, you're familiar with this, is you take the counts. The vertical axis is count, the horizontal axis is categories. And so if I have 100 field failures, there's probably one of them that has 30 or 40, maybe 50 count of a particular failure. I'm going to pick on power supplies. So the category would be power supply failures. The vertical axis would be the count of how many failed. And then the Pareto, in the Pareto principles, that was it 80% of my problems come from 20% of the items, for example, or causes. So the first few components probably constitute the bulk of the counts. And so you sort it by the one with the highest count on the far left, and then it tails off to the right. The theory is that you pay attention to the high frequency items and solve those, and it has the most impact on your product. Now, what's one of the problems with the Pareto analysis? If I'm just doing counts of failures, what's one of the drawbacks of that? Something to keep in mind. Yeah. So that's a good point, Jim. I hadn't thought of that. If something fails often and it takes 3 weeks to fix it each time, that's a more serious problem than if it fails often and it gets fixed in seconds, right? Or related to that would be the cost of the failure. Some things fail and it's a reset and there's no cost other than a lost few minutes of time. Whereas other failures, I have to replace an expensive component. And so cost or magnitude of downtime, those kind of things can be added to Paretos, and you can weight the counts by their impact, their consequences. and it may shift it may be something that doesn't fail very often, yet has huge impact, and it may be worth paying attention to that. So Pareto analysis is one way to use our data to convey the information to help other people make good decisions. What do we need to work on? But keep track of criticality or consequences. Weibull analysis here. Imagine the vertical axis is a probability scale. It's a log scale for Weibull analysis, going from no failure, 0% probability of failure, up to 100% probability of failure. It's a cumulative distribution function. Vertical axis is time. And we get a line on here, just a straight line, if it fits a Weibull analysis or a Weibull distribution. And the slope of that line is very informative, and where it's located on the timeline, likewise, is very informative. Now, if I'm comparing two components, let's pick on, say two power supply vendors, and we get Weibull information from time to failure distributions from both vendors, and we plot them both. The one to the right is a bit more robust. It takes longer for the same percentage to fail. Now, the slope may be different also. Do we want one that doesn't fail for the first 6 months and then they all fail shortly after 1 year? Or do we want one that has a more gentle slope and has a modest number of failures throughout? We can do the math now and sort out which one we want for the time period that we're interested in. And so it gives us a sense of ability to do comparisons. It allows us to look at field data for the different subsystems within our product to say, oh, the power supply is the biggest problem on wear out, or this compressor is. But initially, it's the case and the fabrication of the wheels and so on for the installation. Those have been having problems. It's based on a real situation I was in, where the Pareto, depending on what timeline we were looking at, if we were looking at 2 months of operation versus 2 years of operation, the Pareto analysis changed dramatically. And so by using Weibull of these subsystems, it allowed us to see it very clearly. It also gave us a priority. These are the things most contributing to the overall failures. And it gave us some prioritization of where to work also. So Weibull analysis I find it is intuitive, more so than a blank screen like I've got here, to all kinds of people to understand what's going on with your product. It just takes a few seconds to explain it, and you get into the decision making and making and not doing the analysis you need. Another one is an MCF, mean cumulative function. And the simplest one is just a plot. It's the count of failures, and this is commonly used for repairable systems, versus time. And the intent here is just do a cumulative count. So I put something into service, and every repair action that we have with the system, it ticks up one spot on the vertical axis, and I keep track of time. Now, here's where I'm waving my hands in front of me, but I'm again, apologize, I don't have the pen. The idea, though, is that if that curve, is just a straight line on this, the failures are arriving fairly routinely and regularly, and I could probably project that line and say that I've got, here's how many spares I need or maintenance staff I need going forward. It's pretty predictable. On the other hand, if it's curving up, right, get the system in place, it runs great, I have 1 or 2 failures in the first 6 months. The next 6 months I have 5 or 6 failures. The next year I've got twice as many failures again. The rate of arrival of those failures is increasing, so I'm curving upward. Well, there's something going on here. This thing may have different set kinds of failures that are occurring, but it's akin to that car I had in high school where it's coming apart. It's not, maybe there's a vibration problem, maybe it was just old and a lot of things are wearing out. Whatever it is, it's just an increasing rate of arrival. We can also use it to take decisions on retirement for this equipment, or is our maintenance program working or not working? Um, those kinds of things. Also doing comparisons like with a Weibull plot. If the curve is flattening out as it goes, is that the equipment's actually getting better. It's breaking in, it's working better. The maintenance program is actually improving the performance of the product from one cycle to the next. So it's a quick visual, and it tells us what we need to know about our equipment. It gives us some insights that just the count alone doesn't give us, whether it's Weibull or MCF. It allows us to see what's going on, and this visualization of reliability data or maintenance data is so much more powerful for decision makers. So those are 3 tools to take a look at to do this stuff. All right. So what other tools? So how else do you present reliability data or reliability related data? We've got just a couple minutes here, and I'm going to leave that question out there as I take a look at just my summary slide. Yeah, I'm catching up with some of the comments. One of the things, Sean, I've seen some people get a bit confused with it on occasion. It usually doesn't take too much to explain what's going on to see the patterns, especially when you have something that does a hockey stick kind of approach. It's got a slope that sharply increases at some point in time. And it's either because there's a different failure mechanism that's taking over, or it's is what I've typically seen, is that we had something that was performing fairly well over time in the system, and now it's taking off and dominating it and changing the overall slope of it. What I find with any of these graphic tools, more so with Weibull and mean cumulative function, is it allows us to ask more insightful questions. It allows us to pursue making better decisions, and that's really a key part of it. So not a negative slope, a less than 1, between 0 and 1, on Weibull anyway. On the mean cumulative function, it's a non-parametric. There are algorithms to fit lines to those and make some generalizations about those, but in general, it's the curvature of the slope and mean cumulative function we're interested in. Is it curving up, or is it curving flattening out? On a Weibull, it's very classic. Less than 1 is a decreasing failure rate, greater than 1 is an increasing failure rate. And we can make some. So part of this is similar to CRO-AMSA, the reliability growth modeling. Similar but not the same. It's also much easier to implement. You can, the count versus time, I've used it with software bug tracking. I've used it with maintenance of equipment. I've used it in all kinds of circumstances, especially dealing with repairable systems, in particular repairable systems. But software during development is like a repairable system, so we can see if we're making improvements or not. And so in summary, the bottom line is focus on the decisions. If we're going to monitor and measure something to do with reliability performance, it has to connect in a meaningful way to the decisions that we need to make. And on your product team, on your assembly team, with your vendors, and with your customers. Let's track things that are actually useful. And if they're not useful, stop tracking them. Find something else that's useful. And connect it to the decisions that need to be made. And so there's lots of tools out there. There's lots of ways to do this. Keeping it simple is often the best advice I have. The simple Weibull plots or life distribution plots, Pareto and mean cumulative function as appropriate, are a great starting point. But if you make it, there's 15 different rules for creating this plot, you need a PhD in big data analytics to understand how to interpret it. Well, is that really useful or not for people that need to make the decisions? In some cases it is, right? It's as appropriate. But the connecting it, what you're measuring to why you're measuring it, and how it's going to help inform the information people have to make a good, balanced decision is the ultimate for it. And so that's the basic fundamental. So with that, let me pull up the where to go. I'll go back to the lobby. And it has the downloads for the slides. It has some couple of links there. The chat window is still there. So I should pause and ask, what are your questions? And I'll keep the line open. And I know we ran a little bit over today. And I appreciate all of the chat and input and so on. I saw some conversations going on that it looked like it was well handled, so I didn't even have to jump into it. I appreciate all the support there. Yeah, yeah, the Crow EMSA is useful, but it takes a bit to explain what's going on there. I just use the mean cumulative function. It's count versus time. And curving over, take longer between arrivals of failures is a good thing. It's not too hard to explain. It kind of gets to the same point across. The growth models allow you to estimate your future reliability, so they have some utility with those models. But it's not as easy to convey unless the audience is very familiar with them. Yeah, exactly. I agree, Mark. It's oftentimes we'll use tools in analysis like setting up a physics of failure model. I don't need to explain every detail of this model and all of its interactions in order to say, yes, this will last 2 years or not. Here's the probability. So I might just use the reliability value at different time points rather than showing the entire wobble plot and go with that. Yeah, excellent. Yeah, Supersmith is a pretty good package. I like it. I don't use it as often as I tend to use other packages. My go-to lately has been R, mostly because it's so versatile. It's a bit of a learning curve, so it's not for the faint of heart. It's actually a programming language, and so but you can do really good work with it. Supersmith, Weibull++, Minitab, other tools all have their place, and use them as appropriate. Yeah, thanks, Ojed. Sorry you had some trouble getting logged in at the start. But we'll have a recording in case you want to, hopefully in a day or two. Rest of today is pretty busy, so it'll be a couple of days before I get up there. Thanks, James. Appreciate it. Yeah, sorry about not being able to do the drawings.